Hello everyone, I am Dr. VRAO, Associate Professor and your Chemistry Learning Companion. In the last video, that is Quantum Mechanics Part 2, we dealt with de Broglie's hypothesis and we derived an equation for wavelength of matter waves, or that is usually called as de Broglie's wavelength for matter waves, right? Which is given by lambda is equal to h by mv. Lambda is equal to h by mv, right? And that equation lambda is equal to h by mv. Lambda is equal to h by mv, right? This is the equation for wavelength, or usually it is called as de Broglie's wavelength for matter waves, right? This equation concludes that all moving objects are associated with wave nature. I repeat, this equation concludes that all moving objects are associated with wave nature, but their wavelengths comes out to be insignificant if they have larger masses, right? Their wavelengths are insignificant if they have larger masses, right? And their wavelengths are significant if they have smaller masses, right? You simply understand with this equation lambda is equal to h by mv. So if the masses of the bodies are higher or much larger, then the wavelengths are insignificant, and if the masses are smaller masses, or microparticles, masses of microparticles, this wavelengths are significant, that is considerable, right? Now I shall give you the examples. Right, I shall give you examples. Example 1: a moving car. Right, a moving car is associated with the wave nature, right? I repeat, a moving car traveling on the road, or a moving car on the road, is associated with wave nature. But when we calculate their wavelengths, which comes out to be insignificant, right? And uh, their wavelengths comes out to be insignificant, right? And you just imagine, and I wish to show the video that the car moving on the road, right? Right, in this video you can observe cars are moving on the road, right? So car is a moving object, and that is associated with the wave nature, right? When we calculate their wavelengths, which comes out to be too small, that is insignificant, right? Right. And I shall give you another example. Right, this is the another example, and this is the microparticle electron. An electron is revolving around the nucleus, right? An electron revolving around the nucleus. Okay, this is also associated with the wave nature, right? this you can observe that electrons are in this video. Various electrons are revolving in various orbits around nucleus, right? So that moving electrons or revolving electrons around the nucleus, right, associated with the wave nature. When we calculate the wavelength of the moving electrons, which comes out to be significant, that is considerable, we can get considerable wavelengths, right? So in these two examples, right, 1 minute. Right. In these two examples, one in example one, that is in moving car example, we concerns with the macro objects, right? And in the example two, we concerns with the micro particle, right? So when we concerns with the macro objects, right? That is when we concerns with the macro objects in general, or simply we can call it as we in our daily life, because in our daily life we concerns with the macro objects only, right? So when we concerns with the macro objects, right, we can, when we concerns with the macro objects, we can we can determine accurately the position as well as velocity of the body that we came across. I repeat, right? You don't confuse with my words. You just clearly listen my words, right? When we concerns with macro objects, right? When we concerns with the macro objects, those are also associated with wave nature, but when we calculate their wavelengths, which comes out to be too small, that is insignificant, right? So when we concerns with the macro objects, right, we can we can determine accurately the position as well as velocity of the body that we come across. I repeat, when we concerns with the macro objects or macro bodies, we can determine accurately the position as well as velocity of the body that we come across. When we are succeeded in determining the exact position as well as velocity at a certain instant, okay, consequently we can uh, predict, or we can uh, determine the path of the moving body. We can determine the path of the moving body, right? Right right But when we concerns with the micro particles, for example, moving electron, and an electron moving around the nucleus, an electron moving around the nucleus, right? Right, we cannot determine accurately the position as well as velocity of the microparticle. I repeat, when we concerns with microparticles, we cannot determine exactly the position as well as velocity of the particle, right? So you should keep one point in your mind, that when we concerns with the macro objects, we can determine the position as well as velocity of the body that we came across. So consequently, we can determine the path of the body, right? Trajectory of the body. But when we concerns with the micro objects, we cannot determine accurately the position as well as velocity of the microparticle or momentum of the microparticle, right? This fact is, Heisenberg find out this fact and proposed a uncertainty principle, right? Heisenberg found this fact, and he proposed a uncertainty principle. What this principle? What this Heisenberg uncertainty principle, right? It states that you can find the statement of Heisenberg uncertainty principle on this slide, right? Right? Okay. It states that it is impossible to determine both the position and momentum of a body simultaneously with perfect accuracy, right? This is the statement of Heisenberg uncertainty principle, right? I wish to insist once again, right? It states that it is impossible to determine both the position and the momentum of a body simultaneously with perfect accuracy, right? But you need to insist on this part, that is position and momentum of your body. What body? Which body? Or which particle? Right? Heisenberg uncertainty principle is exclusively for microparticles, right? Not macro objects, right? Micro particle. Heisenberg uncertainty principle is exclusively for micro objects, okay? Right? You don't confuse with that statement, right? You don't confuse with that statement, okay? In that statement we just written a body, right? But that body is not a macro object, okay? That is exclusively a micro particle, right? Okay, so what is this? It is impossible to determine both position and momentum of the body simultaneously with perfect accuracy. Okay, for a layman, he could not understand what the statement is, right? But I shall try to explain what is impossible and what is how this statement is developed, how this statement was established, right? Okay, right, right, right. We know that a moving electron around the nucleus, this is the nucleus, this is the nucleus, right? This is the nucleus, where this is the nucleus. Electron is moving around this nucleus. I told you that electron moving around the nucleus is associated with wave nature, 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 right? Right, wave nature. Now, when we wish to find the exact position of the electron, we need to execute an experiment. We need to perform an experiment, right? Right. I shall explain the experiment in the next slide, right? Oh, 1 minute, please. Right. how this Heisenberg uncertainty principle or the statement was established, right? We all know that electron moving around the nucleus is associated with wave nature. Now I wish to locate that electron. Now I wish to locate that electron, right? So in this slide you can find that, you can imagine this is the nucleus, right? Where the electron is revolving around the nucleus, where the electron is revolving around the nucleus, right? Where electron is revolving around the nucleus, right? Electron is revolving around the nucleus, right? Okay. So now I wish to locate that electron. For example, you know for example, if you lost your stitching pin, stitching needle, right? If you lost your stitching needle in a dark room, what you do? You just you search that stitching needle with torchlight, right? Whenever you incident the torchlight, okay, on the stitching needle, okay, that light is reflected and you can find that a stitching needle. Okay, in the same manner, when we wish to locate the electron that is revolving around the nucleus, we need to incident a light on the electron, right? I repeat, when we wish to locate the position of electron that is revolving around the nucleus, we need to incident a light on that electron, right? But right, so you can observe that this is the incident photon, or incident light. Now I wish to incident that light on this electron, right? That electron is moving around the nucleus. Okay, so this is the original path of the electron. This is the original path of the electron, right? This is the original path of the electron. Okay, right? In this path, electron is revolving. Now I am incidenting a light of wavelength on this electron. But one condition, there is a one such that condition. When we wish to locate the position of the electron, right? The wavelength of the incident light, the wavelength of the incident light should be smaller than the dimension of the electron. I repeat, if I wish to locate the position of the electron, right, then I need to incident a light on that electron. But here the condition is, when you wish to locate the position of the electron, the wavelength of the incident light should be smaller than the dimensions of the electron. Then only you can locate the position. Then only you are able to see that electron, right? If the wavelength of the incident light is higher than the dimensions of the electron, you you won't see the electron, right? If you wish to see the electron, then the wavelength of the incident light should be smaller than the dimensions of the electron. This is the such that condition, right? So now I am incidenting a light of wavelength which is smaller than the dimension of the electron, right? Whenever I incident the light on this electron, right, but the wavelength of this incident photon is very small. Wavelength of the light is very small. So already we know that the light is traveled in the form of photons. E is equal to h nu. A is equal to h nu, right? And nu is equal to c by lambda. Nu equal to c by lambda, and nu equal to c by lambda. So now we are incidenting a light of wavelength, very small wavelength, Very small wavelength means that which has high energy, wavelength is small, that means whose energy, the energy of that light is very high, or very, that has very high energy, right? So we are incidenting high energetic photons. Low wavelength means that high energetic photons. So we are incidenting the light with the high energetic. We are right. We are incidenting a light of high energetic photons, right? So when this light is incident on this electron, right, that electron gains energy from the incident photon. Electron gains energy from that photon, right? Right. And moreover, when this photon incident on this electron, right, it gains energy and it changes its position, right? It changes its position and changes its direction too, so this is the, when incident photon strikes the electron, okay, the path of the electron is changed. This is the new path and velocity of the electron after interaction with the photon, right? After interaction with the photon, the path and velocity of the electron is changed, right? After interaction of the photon, the path and velocity of the electron is changed, right? Right. Now changed. And one more important thing is there, right? When we instant a photon of wavelength h is equal to, right, h by p, lambda is equal to h by p. We know that lambda is equal to h by p. So here there is another relation is established with this equation. Wavelength is inversely proportional to momentum, right? So we are incidenting very small wavelength radiation. That means that is associated with larger momentums or higher momentums, because wavelength lambda is inversely proportional to momentum, right? So when we incident a photon of smaller wavelength on the electron, we are incidenting a photon with higher momentums, and higher energy. When the higher momentum electron or the higher energy photon strikes the electron, okay, its position changes, its velocity changes, its velocity changes, okay, its velocity changes, and thereby from this we can also conclude that its momentum also changes. Now for example, imagine the position of the electron before the photon strikes is x. For example, here is the electron, and when the photon strikes, it changes its position, okay. So from x1 to another position x2, say, for example, say this is another position where the electron is x2, okay. Change in position, we can write that change in position as a delta x. We can write that change in position as delta x. But when the photon strikes the electron, okay, it causes, when the photon strikes the electron, it 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 increases the momentum of electron, right? Because low wavelength means high momentum. When high momentum photon strikes the electron, that changes the momentum of the electron. So here the position changes as well as momentum also changes, okay. Momentum changes means that velocity also changes, because momentum is mass into velocity, mass into velocity. That momentum changes means, that means velocity also changes, right? Okay. So mass into momentum changes, okay. So for example, if you wish to find out the accuracy, find out, and if you wish to determine the exact change in position, we succeeded. Okay, we succeeded. But and if we wish to calculate, or if we wish to determine the change in momentum, then in such case also we will get succeeded. But when we wish to calculate, or when we wish to determine the position as well as momentum simultaneously, that is one by one or simultaneously, we will fail, right? Definitely we failed, right? That how, and there is a uncertainty, and we can calculate the change in position accurately, we can calculate the change in momentum accurately. But when we try to calculate the change in position and change in momentum simultaneously, we failed, right? So this statement is given by Heisenberg uncertainty principle. Okay, that is why it is impossible to it is impossible to determine the position as well as momentum of electron simultaneously with the greatest accuracy, right? Now, greatest accuracy, right? Okay, for example, if you calculate the position with great accuracy, you will get the most uncertainty in calculating momentum. For example, if you calculate the momentum with great accuracy, consequently you will get most uncertainty in calculating the position, right? This is given mathematically, this uncertainty is given by, right, uncertainty principle. Mathematically, that uncertainty is given by, right, that uncertainty is given by, right, change in position, right? Change in position, that is represented by delta x, and change in momentum, that is represented by delta px, where x is the direction in which the electron moves, right? Greater than or equal to h by 4 pi, right? H by 4 pi. So this is the change in position, and this is the change in momentum, right? Right. So when we multiply change in position and the change in momentum is greater than or equal to h by 4 pi, and you can write this is the change in position, and you can write p, momentum, as mass into velocity, as I said earlier. Okay, greater than or equal to h by 4 pi, h by 4 pi, right? And you can write this equation as delta x is equal to delta vx greater than or equal to h by 4 pi m, 4 pi m. This is Heisenberg uncertainty principle in mathematical equation, in the form of mathematical equation, right? This is about Heisenberg uncertainty principle. This, I repeat, Heisenberg uncertainty principle is exclusively holds good in case of microparticles only. Okay, it is not, and in our daily life it not holds good, right? It exclusively holds good in case of microparticles only, right? These two concepts, that is de Broglie's hypothesis and this Heisenberg uncertainty principle, these two concepts paved the way for quantum mechanics. Actually, these two concepts paved the way for quantum mechanics, and these two concepts helped the Schrodinger to derive a wave equation, right? In the next video, we shall discuss what is Schrodinger wave equation and how these two concepts are combined, right? Okay, in the next video we shall discuss those concepts. Okay, if you I hope you understand this Heisenberg uncertainty principle, and if you really find this video is helpful, you please like, share, comment and subscribe, right? Thank you. Right. Thank you for your attention. Right. Thank you.